We are getting closer to the apéro, and you know this because Stephan will talk to us about beer and serverless architectures for ML deployment. He will present a project that he did with Feldschlösschen and on top of AWS Lambda. And yes, without further ado, Stephan, I look very much forward to learning more about beer and serverless architectures.
Thanks a lot.
Let's give him a hand.
I think I better stay over here just for camera reasons. So yeah, welcome all to my presentation. So the title is Serverless Computing, which is, as Klaus already mentioned, what we used to deploy our recommender system that we developed for Feldschlösschen for their Just Drink online shop. First of all, I just wanted to say that it's really nice to be back at a conference with a lot of people in person. So we were here last year as well, and it was just a completely different experience today. So really great to be here, and thanks a lot for being here. Perfect. So I'll first say a few words to myself. So I'm Stephan, I'm a data science consultant at Statworks. We're a data science consulting and development company, and we work with our partners all along the end-to-end data science. So we do it from initial strategy over development projects to academy projects, where we educate and empower your workforce in the fields of data science and AI. And if I'm not working on topics data science, machine learning, and AI, I'm a very sporty guy. I really like playing field hockey, and I'm very into endurance sports. So before we get to the topic, I'd be very interested to hear who of you has already worked with serverless technology and who's familiar with the topic. So maybe 50-50, so exactly. So if you already know it, maybe I can still get a laugh out of you with these two memes I got. I found out so serverless is not no servers, so it just means that we are not straight out exposed to servers, so that is run in the background, but we'll go further into detail about what serverless is later. So generally what I'll talk about to you today is it's a talk about how we can use serverless in deploying data science and machine learning models, and in particular I'll talk to you about a recommender project that we did at Feldschlösschen, which I'll now start off by presenting this project to you. So we will always have the two parallels. One, what is serverless computing? Why is it suitable for machine learning? And we'll have the specific example of what we did at Feldschlösschen. Exactly. So first, the project I'll talk about is, as I said, a recommendation engine. So that was for Feldschlösschen's Just Drink online shop. I don't know, they've been doing a lot of advertisement recently on YouTube. I don't know if you're familiar with the "you just drink" guy. Maybe not from your reaction. That's a pity. It's only tracking me. Yeah, maybe because I hit our website up pretty often to see if our recommender is up and running. Exactly. So yeah, we developed a recommender engine for them. So the Just Drink online shop is their B2C channel, so how they sell to clients directly. So Feldschlösschen is very big in the B2B sector, and this is part of their initiative to transfer also to a more diversified model to also serve the B2C channel. And the situation we met when we first engaged with Feldschlösschen in this project is that their current recommendation state was a lookup table. So if you go to a product site, you would always get static recommendations which were handpicked. So usually that just meant if you take a Feldschlösschen original beer, you would be recommended a Weizen beer and a Braufrisch, for example, and it was always the same. So there were two problems we faced. One was that it should be more dynamic. That means that the customers on the website need a more engaging experience. When they, for example, hit up a product multiple times, they get different recommendations. So for a better user experience, and of course, overall, to drive sales on their online shop. So what we did then is we developed a session-based recommender system. I'll go a bit further into what the architecture is, just that you have an idea of what model we deployed or what we're facing with, so the challenge, what we're deploying. And I've got my first blackout already, that's perfect. And yeah, exactly. So we deployed this session-based recommender system, then we did A/B tests. So we had the old recommender running, we had our recommender running, we compared these two against each other, and after this successful A/B testing phase, we then went on to deploy the model, where we then leveraged serverless architecture. To go a bit more into detail, where the recommendations were used, so we had two places where they're placed on the web shop, just that you get a bit of a feel for when the recommender was used, so when it was called. That is once on product detail pages. That's what we see here. For example, if you're interested in a Somersby beer, then you see all the details for this product and the description, and at the bottom we have this Kunden kauften auch, so other customers bought section, and that is the recommendations which are made by our recommender. The second place is in the basket, so prior to checkout, you also get recommendations based on what you have put into your basket, which then are also an additional incentive then to buy further products prior to checkout. Then the whole thing is deployed as an API, and if you look at usage patterns we have here, so if a person goes to the website, browses around, goes to a lot of different product detail pages, then you have a lot of calls that happen in a short period of time. So if you imagine a time scale, then you have a lot of events that happen as long as somebody's on the website, and they go away. So it's not like single calls that happen, but it's like clustered calls, which we are faced with here. Then what data did we actually base our recommendations on? That was in particular what the people put into their basket. So we analyzed the basket. So if you're in a shopping process, then you click on an item, put it in the basket, you put multiple items in a basket, and the more you have in your basket, the better information basis we have. The reason for this is that their requirement was that this also works if we don't have any personal information for the customer, so it should also work like in an anonymous setup. So we only based the recommendation on the current basket and didn't take further user information or user profiles into account. So this is the most technical slide you will see today. This is the architecture we used, and I just briefly go over it, that you get a feel of what kind of model we deployed there. So this is a recurrent neural network-based model. We have here the 3 different items which are currently in the basket. They are all embedded. And then we have this recurrent neural network, which is called over and over again for these products, leading to a final representation, which is then processed with an MLP to get the probabilities of the different products. And there we then take the top n products. In our case, it was top 4. What's also interesting, maybe, so of course, like in all recommender settings, we have a cold start problem. And because these products are all very in a hierarchy, so we have beers, we have spirits, we have minerals. So these all have a nice hierarchy. So if we didn't have enough observations to train the recommender, we just clustered them together to the next higher hierarchy, and then made a recommendation for that group, and then sampled again out of all elements in this group to make then the final recommendation. So now let's get to the main topic of the presentation. Now we talked about the model, so now you have a feel for what kind of model it was we had to deploy, and also for the use case. So we have these clustered API calls from different users on the website, multiple users. Then you also have the peak times when a lot of users are on the website, and then you have the down times where very few users are on the website. Exactly, so that's the base setting we're working in. So now I'd like to give a brief introduction to serverless computing. Maybe just in advance, what we used were serverless functions in the end, but I'd like to just open the spectrum here and talk about serverless computing in general. So serverless computing is a cloud computing execution model in which the cloud provider allocates machine resources on demand, taking care of the servers on behalf of their customers, which was nicely summarized actually in the memes that I showed at the start. Then, so what are the benefits of this serverless computing model? So first and most obvious is that we're not in charge of provisioning servers. So that takes away a significant amount of complexity as opposed to setting up machines ourselves and then using these to deploy our models. Second is scaling. So due to the fact that we are not responsible to set up this infrastructure, it's very easy to auto-scale, and all these serverless function providers, or the big cloud providers, at least so cloud functions on GCP, AWS Lambda, and Azure functions, all have automatic auto-scaling included, which is very useful for the use case we have at hand with this clustering of clicks that I mentioned before. Third is pricing. So we only pay for what we need. So you're billed for a call that is made to this serverless function and also for the duration that it runs. So if you're not using the API, you're also not charged. So it's also a very price-efficient way of computing. And last but not least is fault tolerance. So if a certain call is made and for some reason the infrastructure or whatever fails, there's automatic retries that are built in. So we also have a certain type of fault tolerance. This is not general fault tolerance. So if you, for example, have a database connection which is initialized, it won't be closed. That's a risk that you still have, but you have general fault tolerance just by retries which are automatically triggered. Good. Now, next is, we talked about serverless now. Why is this a perfect match for machine learning inference case, or why can it often be a perfect match for machine learning inference? Number one is simplicity. So if you're doing machine learning development yourself, we do a lot of iteration. And so the simplicity, just that we're not responsible for this whole part of deployment as well, makes working with these serverless functions very easy and very handy for us. And the fact that a lot of these solutions are now based on containers as well leaves us with the task of just building a container, and then the whole subsequent deployment process is taken over from the cloud providers from there. And second is auto-scaling. So as I already mentioned before, machine learning applications, as the one we're treating, typically have highly varying workloads, and this can automatically be tackled by the auto-scaling functionality of serverless setups. So if everything is perfect, why is it not used everywhere? There's, of course, one downside as well, and this is so-called cold starts. So if we look how a serverless function like this works, we have these 4 steps. So first, the code has to be downloaded. Then this is actually back to serverless doesn't mean no servers, but it just means we're not exposed to it. So these are the steps that then run in the background. So code is downloaded, then we start a new execution environment, then the initialization code is run, and finally the handler code is run. And if we make a serverless call, then the infrastructure which is set up, so the machine which is set up to treat our case, is kept warm or is kept ready for a certain amount of time. So these 2 steps at the top, if we make 2 subsequent calls, are not executed multiple times, but then you have a shorter execution time because only the 2 bottom steps are executed. So cold start actually means that you have an extra time it takes to run your function call because infrastructure has to be set up in the background. And this can take anywhere from seconds to minutes. And in our case, when we have a bigger machine learning model, so the deep learning model that you saw beforehand, this can take a significant amount of time and took up to minutes in our case. And if you imagine we have a real-time use case, and if then somebody comes to the website, then clicks, doesn't see a recommendation, wait, 2 minutes later you see a recommendation, that's simply not good enough. So what can we do about it? So there are 2 options. One is a bit more of a hacky version which exists, which is called lambda warming or serverless function warming, which means we just, in a regular time interval, send empty calls out to the function just to make sure that the instances are kept running, but we are, of course, also charged for these calls. Second possibility, which doesn't exist that long yet, is called provision concurrency. So that you just say, we have a minimum number of machines which are running, and that can be, for example, set to 1. And then if you have, then you never have this long waiting time. You may initially, when you have a rise or a surge in calls, you'll be slower at the start than you usually would be, but you never go into this realm of minutes of waiting. So in the upscaling phase, you then have this certain amount of time where one instance alone has to treat all this traffic. However, this scales up then after, say, a minute in our case, and then you're back to your original speed. Exactly. So these are the two ways, warming and provision concurrency. So problems, of course, are if you have an instance that's running all the time, that has an influence on billing as well, or so on pricing, because you have one machine that's running. But in a case where real-timeness is important, this is definitely a trade-off that you have to make. And the second is, as I already mentioned before, that this cold start phenomenon also applies to scaling. And so, in general, we say that this warming or this avoiding this cold starts is necessary if you have large setup times, which we now had with a minute. And the second is when real-timeness is important. So if you have some back-end job which is runs on serverless, that's no problem. However, due to the real-time nature of our problem, we had to make sure that this cold start case never occurs. Then I'd like to show you our particular setup. We had now for the Felch lesson just drink recommender. So on the left side, you have the browsers. So that's the people which are surfing on the just drink side. Then the initial traffic is rerouted by an API gateway. Then we have, so this is a specific setup on the AWS cloud now. So Felch lesson uses AWS very heavily. And this is the setup we then actually built for them. So you have the API gateway as a first instance on AWS where all the traffic hits in. Then we have one or multiple Lambda functions which are responsible for processing the call and for executing our machine learning model for processing the different calls. And in the background, we have a Docker container which these Lambda functions are called from. Of course, we have to make sure that our solution is updated regularly. So they introduce new products. They take products out of their, you say stock for an online store, I'm not sure. And then reintroduce products as well. So we have this regular model training that we do. That is a training pipeline that runs on SageMaker. I wouldn't go into further detail about that now, but we have monthly retraining there. And then we also redeploy this on a regular basis. So we have our two parts. On the left, we have the serverless setup, which handles the traffic based on the model container that we have. And on the right, we have a regular model training. So the last step is what happens here in between the model training and the model container.
I didn't get that. Could you try again?
I hope it's not the same for you. And if it were like...
What do you mean?
Okay, very sorry about that. Siri, I'll turn you off now. That was actually pretty perfect timing, wasn't it? Yeah, so this is the delivery pipeline we implemented. We have various steps here. So first, we have to prepare the artifacts. So we've run this model training on SageMaker. Then we have our model checkpoint and all the lookup tables for the correspondence between article numbers and articles, etc., which are then have to be prepared. Then we have our build process. This runs on AWS code build in particular. So the whole build pipeline runs on code build. Then then the model container is built from that. So the Docker container is built. Actually, even more in particular, we use the serverless application model by AWS. Then various tests are run. So both after the model training, we ensure that we have good enough performance on our test set. If not, the model is not freed for deployment. And here we also test different API calls so that everything else, so how our response is wrapped, that is correct. And finally, if all these steps are cleared, then we go on to deploy. So finally, if I get a last chance to tell you my main takeaways. So one would be a more general thing. So if possible, when deploying solutions like this, use standardized cloud services. This can save you tons of time, and they have put a lot of engineering work into making these services optimal as possible for us to use. Second is that in the serverless setup is ranks very high in usability. So as we are taken away from the complexity of the servers as such, we can iterate way quicker when deploying machine learning models. And the third is, when you use serverless technology, cold start is always a problem which you have to be very aware of. But as I presented beforehand, we have multiple ways in which it can be counteracted, so both warming and provision concurrency. So we started with memes, we'll end with memes. In summary, serverless is a price-effective, scalable way of deploying machine learning models in the cloud. So if you implement your next project, think of maybe if a serverless approach would be something for you as well. And maybe if you don't remember me, you might remember Drake telling you, manage servers. Nah, let's go serverless. Thanks a lot, and I'm glad to take any questions you may have.
Very cool. So as a small gift for your next beer.
Thanks a lot.
So we're gladly taking questions. There are two. Gabriel, you save away.
Thank you for the presentation. I have a question from your 9th slide, which is related to the machine learning architecture.
Yep.
So my first question is that did you have any specific reason not using transformer? Yes. And the second question is that how do you your embedding works for your products? Is it kind of one-hot encoding, or do you learn this kind of embeddings for the different products that you have?
It's an end-to-end approach, so the embeddings are learned as well. So we have at the beginning of a transformer model, you have your one hot, which is then transformed into an embedding, and that is learned also end-to-end in the whole process. Okay, and do you also have a kind of feature vector for the different products? For instance, I could imagine some customer that are interested in gingers. Maybe if it is exist in the drink A, if it is exist in the drink B, they could be interested to both of them. So do you also kind of? You mean explicitly if we did manual feature engineering for? Not feature engineering, just actually a list of feature for every product, maybe the content or the ingredients of the different drink that you have. Yeah, no, so the only thing we used here is really just the ID. So we learn based on the ID, and then just the sequences of products is actually the signal that we use. That would be possible in the next step. So possible extensions are that you take into account further into the history what a user bought, and also make user profiles. That would be one direction, and the other one would be maybe a bit bring the content based or the item perspective into it. It's currently not done. What we do additionally to here, which is not on the slide, is seasonality. So that was important. So we also take into account seasonal factors by fitting in or by feeding additional a seasonality component through the network besides the item embedding. Yeah.
Thanks. So I have a question to the scaling behavior. If you probably go to the architecture slide. Yep. So let's imagine that we are not in a cold start scenario, so that we already have our first Lambda running and API gateways routing there. Yep. And first question is, how does Lambda in the background determines if there is a need for a second instance? That's the first question. And second question is this second instance also going to be started from cold start, or is there kind of a fork happening from the first one to the second one? That's second question. And third question is, sorry, at what point is API gateway going to be rerouting the requests to the second Lambda?
Yeah, so actually, maybe it's a bit deceiving. So Lambda does all this distributing of the traffic itself. So it's very tightly coupled, the gateway and the Lambda. So this is something we're not exposed to either. So this is also serverless. In the serverless principle, this is something that is Lambda takes care of it, and they have their protocols in which they optimally assign this traffic. So you have a certain threshold which you can also steer. So you can also give say from this amount of traffic on, I want new instances. But our experience was that just leaving Lambda do their job was way good enough. So I can't exactly tell you what they do in the background. I'm pretty sure as well that it's more like that's not publicly available. I might be mistaken, but yeah. So that's actually something that runs in the background. Second question was concerning cold start for second instance. Of course, you have that. Yes. So the first that's what I mentioned before in cold starts, that you also have it for any further instance that comes. So if you have a surge in requests, then they would first all be treated by the first function, which then makes it slightly slower, but not as slow as if you had to do a complete cold start. So it's actually like a bit stretched out, that you initially are slower with treating these requests until the cold start period is over, and then it can be distributed over the multiple instances. And third question.
But you already answered when it's going to be rerouted.
Yeah, okay. So does that answer your question? Thank you.
Further questions? There are two.
Yeah.
I also have two questions. So the first question is which analytical platform did you use? So was it something AWS native, or where was your code actually for the model?
Yeah.
So that's the first question. And the second question, so what was the payment model? So in model training and exploration, you shift around data, and that can be very expensive in the cloud, or at least in the Azure cloud, as an example. What I know, what was your experience with AWS there?
So maybe for number two, the severity in this project was not that large because we don't have that large amounts of data. So we have only a few years of history, and so it's not in that range that you would really excel in cloud costs. So that was not really a big issue here, but in general, we did all our training on SageMaker, and they already have their other databases in AWS already, so the traffic in between is not as expensive as if you have to source it from somewhere else and have ingress traffic. And the first question was regarding, can you give me one word? Yeah, okay, yes. So you have multiple ways in which this is possible. One is to use like a model that AWS provides already, so a container that they provide, that they have actually for most frameworks already. So you can have a gradient boosting model that you train directly, that where you then only give them the parameters and it is trained. Then you have bring your own script, where you actually have a container that they provide. And the third case is that you bring your own container, and that is run then on SageMaker. And we were in the second case, so we used a TensorFlow container that AWS provided, and then had our own training scripts, which then ran on this TensorFlow container provided by AWS. Yeah. Thank you.
There were more questions in the front, right? Oh, there's one more in the back.
Maybe it's related to that question. So
Yep.
how many items are you actually recommending for?
Yeah, so we have 1,500 items in total. Hey, thanks a lot for all your questions. This is really
Yeah, there's
cool
so
and
many.
very engaging.
I have two questions. Like the first one is, you said no personal data is involved. You probably still use a cookie or need a cookie for all the products customer use.
No, actually not, because we just have, when the customer is there, it's all the products which are in the basket, which have to be stored anyway. That's based on, okay, actually, we don't need anything additional. So this is what they track anyway. So we don't need, you don't have to be freed to use other personal data. So usually, there are other recommender approaches where you really take in a user's history or gender, etc. And we don't have that here at all. So it's really only anything that you put into the basket is then what we treat as information that we have. So initially, we don't know anything about you. Then you put one item into the basket. Then we use that in combination with putting like pseudo items into the basket based on where you currently are on the website, but not according to your, say, we don't track like where you click, for example. It's really only what is in the basket.
Okay.
Maybe it's a definition question, but I'll be glad to discuss
you can do
that
it
more
on
in
the
detail
back
with
end
you
if
afterwards.
it's, in the basket. So, and the second question is, like, did you think of our architectures? I think it's rather complicated, as we in the company also have recommender engines that are much simpler than this case.
Yeah.
And have you thought of that?
Yeah, we of course looked at other architectures as well. Like any classic kind of collaborative filtering methods, etc., fall away just due to the fact that we don't have this information. So actually, based on only the items in the basket, this was more or less the go-to approach that we found. So we did take into account a lot of other approaches as well, but due to the fact that we have to do it without additional information at query time, this was the model we got. So we looked at a lot of other things, but specifically now for this use case where you don't take other data into account, this was more like the go-to way.
Cool. I would like to ask the questions to come up individually because there's a break right now and I don't want to keep all the others waiting. So have a beer downstairs, take a break. We'll reconvene at 3:15 here in this room.